Welcome to this presentation, Utility Functions Part 3. In this presentation, we're going to calculate basic expected utility and finally combine the idea of expected monetary value with the utility topic discussed in this module. The main objective in utility theory under uncertainty is to maximize expected utility. Practically speaking, in reality, you might deviate from whatever your decision tree might tell you. But if we're using expected utility, the assumption is, at least when we're doing an analysis, is that you're going to go with the option that yields the highest utility, the highest expected utility. I'll give you a simple example here. Let's say the decision maker, has the following utility function, and it's an exponential function. So it's a simple curve that many of you probably have used in your previous math courses. So given that this is my utility functions, since I already have the function, I can use this directly to evaluate, convert monetary value directly into a utility value. So let's say the individual is faced with the following two alternatives. Alternative one is a certain cash amount for $5,000, so it's a 100% guarantee of $5,000. And then alternative two, there's different probability associated with these monetary values. So there's a 20% chance that the decision maker will lose $10,000, 20% chance that it'll yield nothing, 20% chance of $10,000 gain, 20% chance of $20,000 gain, and a 20% chance of a $30,000 gain. So given the choice of alternative one, which is 100% guaranteed, alternative two is basically a lottery, right? Which alternative would this decision maker choose between these two if we were to use expected utility? Using the utility function, what is the best alternative between these two for this specific decision maker? As we continue our analysis here, we're going to start with alternative two first. We have a given utility function, so we don't have to do any utility elicitation or anything like that. We already have the function. Now, given the set of monetary values that are available and the different probabilities, we should be able to come up with an expected utility. Now, I want to make sure you understand that we're not using the monetary values directly here because we want to make a decision based on the decision maker's utility, their utility function. Okay, so we have to convert each one of the monetary values into a utility value. So we have the set of monetary values, negative 10,000, 0, 10,000, 20,000, 30,000, and we can see the associated utility values there. And I'm gonna give you the calculations for these. So again, for negative 10,000, the utility value is negative 1.718. Where is this coming from? I'm just simply using my utility function that's provided. So, the W here is the monetary value. That's my W. That row is my W. Okay, so I'm just plugging that in directly into that function. So I'll show you each one here. So the utility for negative 10,000, if you plug in negative 10,000, you're going to get roughly negative 1.718. If we plug in $10,000, okay, you're going to get 0.632. If you plug in $20,000 into that function, you're going to get 0.865. And if you put in $30,000, you're going to get roughly 0.95. Obviously, if you plug in 0, you'll get 0. Okay. So based on this, then again, this is the utility value associated with that monetary value using that utility function, right? Okay. Now we have to calculate the expected utility, right? So we have to use the utility values, okay, this row right here, okay, and then we have to then use the probability values, right? So it's really, you're taking these two rows and doing a sum product, right? So it's negative 0.2 times, so this, let me highlight here, negative 0.2 times this value plus negative 0.2 times 0 plus 0.2 times 0.632. So that's what this expected utility calculation on the bottom line is showing you. Okay, so the expected utility at the end ends up becoming 0.1 0.146. Okay, so that's the expected utility for alternative number 2. If the decision maker were to use alternative 2, the expected utility for that decision is 0.146. Now, what's the other alternative? It's alternative 1, right? So alternative 1, the decision maker has a 100% probability of getting $5,000, right? So we again use this monetary value, plug it into a utility function. Okay, so you plug in $5,000. Okay, we get a value of 0.393. Okay, so if we're using expected utility, which one do we prefer? Alternative number 1 yields the higher expected utility, so therefore we prefer alternative 1 over alternative number 2. On the previous calculations, we saw the evaluation of the expected utility of alternative 1 and alternative number 2, and we concluded that alternative number 1 is preferred. Now, just to contrast this, I'm going to do the same calculation here, but taking the expected monetary value instead. Same type of expected monetary value, things we've done in the past modules, but I'm going to show you the difference here with what we did with expected utility. Okay, so again, the results are the same, right? Same monetary value, same probabilities, same utility values associated with each monetary value. But now if we're evaluating this based on monetary value, what would it be? Okay, so we've done this enough where hopefully this is very simple for you now. The expected monetary value here is we're now looking at these two rows. Okay, the utility row now is not relevant because we're taking just simply the expected monetary value. Okay, so the EMV here is going to be 0.2 times minus 10,000 plus 0.2 times 0. So again, I'm just reading these two rows, right? Okay, just finding forgetting the sum product, right? Okay, so again, 0.2 times 10,000. Okay, I'm just gonna put dot 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 here because I don't want to keep writing this out. So next pair will be this, next pair will be this. You put all of this together, you should get 10,000. Okay, so the expected monetary value here is 10,000. Okay. Now, when we use the expected utility, we had 0.146 for alternative 2. Okay. The expected monetary value was 10,000. For alternative number 1, we also calculated the expected utility to be 0.393. But the EMV for alternative number 1 here is a guaranteed 5,000, so it's just 5,000, right? So if we take the EMV approach here, then the preferred alternative now changes to alternative number 2, right? So because we want, 10,000 is a higher expected value for than 5,000. So if we were to just use EMV instead of expected utility, our preferred alternative will be alternative number 2 rather than alternative number 1. As a follow-up question, if we want to know what the cash amount equivalent to the utility value is, we can. Okay, so for alternative number 2, for expected utility of 0.146, you can work backwards and calculate what W is. Okay, it ends up being 1,574. So this is much smaller than $5,000 for alternative number 1. So when we used when we used expected utility, we came up with, we concluded that we wanted alternative number 1 over alternative number 2 because it had the higher expected utility. The cash equivalent or the monetary value equivalent is also confirms the same outcome, right? So it's the cash amount equivalent for alternative number 2, it's got a lower value than the cash equivalent value for alternative number 1, which is $5,000. So again, this confirms what we got earlier. Hopefully this kind of clears up any confusion about these two methods. One, in the previous example or the previous calculation, we made our decision based on expected utility. In this example, we made our decision based on expected monetary value. And we also did an additional calculation on what would have been the monetary value at the expected utility value of 0.146. We now proceed to a more elaborate example, buying fire insurance. So let's say a homeowner is considering buying fire insurance. Assume that the homeowner has no outstanding mortgage or loan against the home. The probability of damage from fire in any given year is 4%, and the amount of damage is estimated to be $80,000. Their fire insurance premium, let's say it's $900 per year. And this is for simplicity. We're going to make the values a lot easier. We're going to make some assumptions to make an analysis a lot easier. Let's assume that the annual deductible is $600. So this is the amount that the individual will pay for any claim. So even though they have fire insurance, if a fire happens, there's damage, up to $600, the homeowner would still have to cover. Assume that the homeowner's total wealth, including the home, is $140,000. And let's say the homeowner's utility function is given by an exponential function as shown there. And ultimately then we want to decide, or we want to help the homeowner make a decision, should the homeowner buy fire insurance or not? And we'll be taking this as a expected utility approach, and we could also take this as expected monetary approach. And we'll see what our analysis shows here. Now let's first consider a case where the homeowner does buy fire insurance. So to be clear here, if the homeowner buys fire insurance, doesn't mean that there will be a fire or there will not be a fire. It simply means that homeowner has paid the premium and they are covered for their coverage. They have some kind of coverage if there were to be a fire. Okay, so let's consider the case where there is no fire. Okay, so if there's no fire, the impact on the homeowner is that they would have still had to pay the insurance premium, which is $900. So their wealth decreases slightly because of the premium they would have to pay. So the wealth here, W, it decreases from 140,000 by $900. It goes to $139,100. So for this value, we can calculate the utility using their utility function. So we apply the utility function to get their utility value, which is 0.9846. This is the utility if the homeowner buys fire insurance and there is no fire. But if there is a fire, then the homeowner would have to pay not just the premium, but they would have to pay the deductible based on that claim. So their wealth now would be $140,000 minus the premium, $900, minus $600 for the deductible. So their net result is $138,500. The utility for that value is 0.9843. Okay, so based on those, we can kind of figure out what the expected monetary value and the expected utility value would be for this situation. So let's look at the probability tree here. So this is looking at pure monetary value. There's a 4% chance of fire. If there is a fire and the homeowner has insurance, then their net wealth at the end will be 138,500. If there is if there's no fire, then their net wealth is 139,100. So the expected monetary value for the situation where the homeowner does buy fire insurance is 139,076. So this is the expected monetary value for buying fire insurance. Now, on the flip side, if we look at the situation, but look at the expected utility perspective, take the expected utility perspective, we again have the similar looking chance note here in the probability tree here, okay? But instead of having these monetary values here, we have the expected utilities, right? For the case where the homeowner buys insurance and there's no fire, the expected utility was 0.9846, this value over here, okay? For the case where the homeowner does buy fire insurance and there is a fire, the expected utility was 0.9843, which is this value here. The probabilities are unchanged, 96% for no fire, 4% for fire. So then the expected utility is 0.9846. Okay. So, taking this though, we could also calculate what the monetary value of this expected utility would have been as well. Okay. So as an add-on, I can do that as well. So we're going to take the expected, we're going to take that utility function, u equals to 1 minus e to the negative 0.0003 times w. That equals to the expected utility 0.9846, right? So this value is that value right there, okay? And then we're just going to solve for w, right? We're going to just solve for that w variable, okay? And it ends up being about 139,075.8, okay? So this is the analysis for the case where the homeowner does buy fire insurance. Now we got to contrast this to the case where the homeowner decides not to buy fire insurance. We now look at the case where the homeowner chooses not to buy fire insurance. Okay. So if the homeowner chooses not to buy fire insurance, and that means that doesn't mean that there will be a fire or there won't be a fire. It just simply means that they don't have insurance coverage if there was a fire, right? So let's assume that there's no fire. Okay, there's no fire. Their wealth is still 140,000. It's unchanged, right? We can now find the utility value for this 140,000 simply by plugging into the utility function, which is 0.983. I'm sorry, 0.985. Okay. Now, if there were a fire and the homeowner doesn't have insurance, then they would have to be responsible for the repairs. So in our case, we just assumed to be $80,000, right? So with fire, their wealth would then decrease from 140,000 to $80,000. So your net wealth at the end will be $60,000. If you plug this again into the utility function, we get 0.8347. Okay. Graphically speaking, you can draw out the probability tree here. If you take a pure monetary value, expected value, if the homeowner decides not to buy fire insurance and there's no fire, the net outcome is still 140,000. There's no change in their wealth. But if there was a fire, they have to pay $80,000 in repairs, so the net wealth decreases by 80,000. The associated probabilities are on the tree: 96% for no fire, 4% for fire. So then the EMV here ends up being 136,800. Okay, so this is the expected monetary value for not buying. Okay. Now, if you were to look at the expected utility perspective, okay, if you were to if the homeowner chooses not to buy fire insurance and there's no fire, the utility for that decision is 0.985. Okay, but if there is a fire, the expected utility net is 0.8347, which is this value over here. Okay, the probability of fire and no fire is unchanged. Okay, so then the expected utility ends up being 0.975. Okay, so you can then get the monetary equivalent of this expected utility of 0.975. So again, I take this value, set it equal to my utility function, and then solve for W. Okay, it ends up being roughly $128,000, $108,762.20. So then we could actually look at this and see how big of a difference is this relative to the monetary value. Okay, so the expected monetary value for not buying was $136,000 and $136,800. The expected utility for not buying was 0.979. The monetary value of this is $128,762.20. Okay, so what this implies is the difference between the monetary value, the pure monetary value, and the equivalent monetary value when you equate the utility function of this person, the difference is roughly just over $8,000. Now, we could summarize all the results here and then come up with what the best decision will be for this homeowner. Okay. We can also calculate the difference between the EMV and the monetary value from the utility value. So we've actually already done this, but I'll summarize it here. Okay. So the first event that happens in this situation is whether or not the homeowner buys insurance or does not buy insurance. Okay, that's the first event. It's a decision node, right? Okay, and then the chance nodes are either there's a fire or there's no fire, right? So that's my chance node, and you get the different outcomes here, right? So you can find the expected monetary value, okay, and it's $139,000.76. I'm sorry, $139,076. Okay, so obviously that's bigger than the do not buy insurance branch. So the optimal decision here is to buy insurance. Okay, the other tree at the bottom is if you take the utility function perspective. Okay, so it's still the events are the same order, right? You either buy or you don't buy insurance. Okay, and then you have a chance node of whether there's a fire or there is no fire or there is a fire. Okay, and if you don't buy insurance, same thing, right? You either have a fire or you don't. Okay, and we have the equivalent monetary values. We converted these monetary values to the U values or the utility values. Okay, so those are provided there. Okay, we did this on a different previous slide. Okay, then we can calculate the expected utility at each one of those nodes, which did on the previous slide. Okay, so we're comparing the buy insurance branch against the do not buy insurance branch, or I was going to pick the higher utility value. Okay, which is buy insurance. And we've converted the buy insurance utility value, 0.9846, to the monetary value, which is $139,075.80. So if you look at both of these situations, both of these trees, the optimal decision is to buy insurance. Another way of kind of looking at this is the following. If you look at the buy insurance option, the difference between taking the EMV approach and taking the expected utility and then converting it to the monetary value, the difference is very, very small, right? It's almost negligible, right? Okay. But for the do not buy insurance branch, okay, the difference in the monetary value is quite large, much larger, right? You're comparing 136,800, and you're comparing this value over here, okay? If you were to convert this 0.979 to a monetary value, again, in the previous slide, it's roughly $128,762, right? Okay, so if you're comparing those two branches, the difference is quite large. It's basically over $8,000. Okay, so do not buy insurance has a much higher difference. So in this case, the homeowner should buy insurance. This is the end of the presentation. Thank you for watching.